All right, let's just jump right into this explainer. Imagine stepping into a completely futuristic, Ultra HD digital lab. Picture floating ions, glowing 3D molecular structures, and these holographic chemistry formulas just spinning all around us. Today, we're decoding the exact real-world electrochemical mechanics you actually need to nail those 2026 CBSE board exams. So think about it. How do we harness the invisible flow of electrons to power the modern world? Well, in this explainer, we're going to trace the literal cinematic journey of a single electron. We'll watch it go from its spontaneous release in a bright, glowing chemical reaction all the way to how it mathematically powers everything. I mean, from the smartphone in your hand right now to massive space shuttles, and literally even the sensory signals traveling through your own brain. It's wild. Okay, here's our mission briefing for today. We're going to systematically break down this entire chapter. We'll start with the core of electrochemistry, step inside the Daniell Cell, break down the Nernst Equation, explore conductivity and electrolysis, check out real-world batteries and fuel cells, and finally, dive into the science of corrosion. Sound good? Let's get into it. Section 1, the core of electrochemistry. Let's start with the absolute foundation, which is basically the logic of how chemical energy and electrical energy interact. Now, this perfectly illustrates the two fundamental pillars of our whole subject. On one side, we have galvanic or voltaic cells. Think of these as the generators. They take spontaneous chemical reactions and convert that released energy directly into electricity. Then, on the flip side, we have electrolytic cells. These are the consumers. They take incoming electrical energy and actually use it to force a non-spontaneous chemical transformation to happen. It's essentially a perfect two-way street of energy transfer. Moving to section 2, inside the Daniell Cell. Let's really zoom in here down to the atomic level and step inside a classic example. Take a look at the zinc electrode on the left and the copper electrode on the right, both dipping into their respective glowing electrolyte solutions. Now, see that connection in the middle? That's the salt bridge. This U-shaped tube is literally an absolute vital subatomic traffic controller. It allows the ions to flow and maintains electrical neutrality, all without letting the two solutions physically mix together. Step by step, we can watch this whole cinematic reaction unfold. First up, at the zinc anode, we get oxidation. The solid zinc atoms shed 2 electrons to become zinc ions, and they just dissolve right into the solution. Next, those released electrons, you can see them glowing electric blue right there, they surge through the external wire. Finally, over at the copper cathode, reduction happens. The copper ions in the solution actually grab onto those 2 electrons and deposit themselves as solid copper right on the electrode. So oxidation at the anode, reduction at the cathode. Okay, so the crucial point is this very specific number, 1.10 volts. When the concentration of the zinc and copper ions is exactly unity, meaning just 1 mole per cubic decimeter, this exact Daniell Cell setup generates a precise standard electrical potential of 1.10 volts. And here's the crazy part. If you apply an external opposing voltage greater than 1.10 volts, you can actually throw this entire process in reverse. You literally turn our galvanic cell into an electrolytic one. All right, section 3, Nernst Equation and potentials. Let's shift over to the mathematics and see how we predict all this electron movement. You know, to measure anything, you really need a starting point, right? Think of the standard hydrogen electrode, or SHE, as our electrochemical sea level. It's basically a platinum electrode coated with platinum black, sitting in an acid bath with pure hydrogen gas bubbling through it at exactly 1 bar of pressure. By international agreement, this specific setup is assigned an absolute baseline 0 potential at all temperatures. Every single other electrode voltage we talk about is just measured relative to this exact 0 point. So with our baseline set, calculating the overall cell potential is actually beautifully simple. The standard potential of the cell, E cell, is literally just the standard electrode potential of the right-hand cathode minus the standard electrode potential of the left-hand anode. That's it, just right minus left. But what happens in the real world when concentrations aren't just a perfect 1 molar? Well, that is exactly where the Nernst equation comes in. For your exam, you absolutely have to memorize these holographic variables floating up here. R is the gas constant, T is temperature in Kelvin, F is the famous Faraday constant, which represents the charge of 1 mole of electrons, and N is just the number of moles of electrons transferred in the reaction. The Nernst equation takes these constants and lets us calculate the exact electropotential at literally any concentration imaginable. Moving on to section 4, conductivity and electrolysis.
Now that we have the potential mapped out, we've got to understand how these ionic solutions conduct the actual current.
So when we pump electrical energy into an electrolytic cell to force a reaction, how do we actually measure it? Faraday's laws of electrolysis give us this elegantly simple equation. Q equals I times T. The total charge Q in coulombs is just equal to the current I in amperes multiplied by the time T in seconds. This lets us quantify the exact amount of charge needed to deposit a very specific, calculated amount of metal during a reaction. It's kind of the perfect bridge between electrical physics and chemical mass.
All right, let's zoom back out from the equations for Section 5, batteries and fuel cells. We're going to apply these electrochemical principles to the devices that literally run our world. When we commercialize all this science, we basically get two main types of batteries. First up, primary batteries. These are your one-and-done types. The reaction happens once, the chemicals get depleted, and yep, the battery dies. The classic example is the Leclanche dry cell that's probably running your wall clock right now. Then, on the bottom row, we have secondary batteries. These are your rechargeable heroes. By passing a current in the opposite direction, we completely reverse the chemical reaction. This includes stuff like the lead storage battery in cars and the tightly coiled jelly roll setup of the nickel-cadmium cell. And that brings us to fuel cells, which honestly represent the absolute future of energy. Instead of just storing chemicals inside, a fuel cell continuously takes in external fuels like hydrogen, methane, or methanol. By converting the chemical energy of combustion directly into electricity, we totally bypass traditional thermal plants. The result? A massive 70% efficiency. And the best part? A hydrogen-oxygen fuel cell produces literally zero pollution. The only exhaust product is just pure, clean water. How cool is that? Finally, we hit Section 6, the science of corrosion. Let's look at the dark side of electrochemistry and see what happens when these spontaneous reactions attack our infrastructure. You see, rust isn't just decay. It is an active, microscopic electrochemical war. Just imagine a simple water droplet sitting on an iron bridge. That tiny droplet essentially sets up its own destructive galvanic cell. At an anodic spot, the iron oxidizes and releases electrons. Those electrons travel through the metal to a cathodic spot where oxygen from the air gets reduced. This tiny, spontaneous little cell actually generates an overall potential of 1.67 volts, slowly eating away the solid iron and turning it into flaky, hydrated ferric oxide. Or, what we just call rust. But luckily, electrochemistry also provides the cure. We can use barrier protection like paint or an inert coating of zinc or tin. But for sure, the most fascinating method is the use of sacrificial electrodes. We can intentionally attach a much more highly reactive metal like magnesium right onto our iron structure. The magnesium essentially sacrifices itself. It corrodes away entirely, so the structural iron stays completely protected. It's a seriously ingenious electrochemical trick to save our buildings and bridges. So as we wrap up this explainer and power down our digital lab, I want you to look at this final question. If electrochemistry drives the sensory signals in our brain, the batteries in our pockets, and the hydrogen fuel of tomorrow, what new electrochemical application will you discover? As you gear up for your 2026 board exams, just remember, you aren't just memorizing dry formulas here. You are literally learning the code that powers the universe. Keep that curiosity alive. Keep studying those electron flows, and I'll see you in the next explainer.